Hello everyone. In this video we're going to discuss a very important group of functions called one-to-one functions, which also are associated with another concept called inverse functions. In our last video we discovered what functions are, and we also discussed operations on functions and the composition of functions. We are going to rely on those topics in this video, so please make sure that you have watched that before you try to understand this video. If you recall, a function f is a rule that assigns to each element of a given set, such as the one here, which we call the domain, one element and only one element from another set, which we call the range. Now we know that the first elements here should never be associated with more than one output. This is an example of another function. There's no problem with two inputs having the same output, but we don't want one input to have more than one output. So both of these are functions, but clearly there is something different about them. If you notice, in this function f, each input is indeed associated with only one output, but also no two inputs have the same output. Whereas here, yes, each input does have only one output, but A and B happen to have the same output. The difference that this makes is that we say the function f is reversible. In other words, if I ask you what input did 2 come from, it's easy to look at this diagram and say, oh, it came from B. But if I ask you the same question about the function g, you'll say, well, I'm not sure where the input 1, for instance, came from. It could have come from A or it could have come from B. So this makes g not easily reversible in the style of f. So functions like f, where no two inputs have the same output, are called one-to-one, and they're extremely important because of their reversibility. So first of all, we reverse f, and we have a special name for that function, which basically switches the domains and ranges. In other words, instead of the inverse function, which is written here, this notation here is not to be confused with the exponential notation, which would turn it into 1 over f. This is a new format for using this notation, and we call it f inverse. And basically, whereas f sends A to 1, f inverse will send 1 back to A. It'll do the same with 2 and 3. It'll send them to the original inputs they came from. This becomes a function in its own right, and it is called f inverse. Its definition is based on the fact that when f of x is y, we know that f inverse is going to send y back to x. So f inverse of y will be x. And for the inverse function written here, we can also put it in standard functional notation, which is a set of ordered pairs. So we can write it as the ordered pairs 1a, 2b, 3c. Notice it's the exact reverse of the definition of f. The domain of f, if you recall, is the set containing a, b, and c. And if you see, that's the range of f inverse. So this is why we say inverse functions exchange domain and range. Now the range of f, if you recall, was 1, 2, 3, which is the same as the domain of its inverse. These are very simple concepts, but extremely important. Please spend enough time on this screen till you completely understand these basics before we proceed. The functions we discussed on the previous screen had finite domains and finite ranges. Most of the functions we will be looking at in mathematics will have infinite domains and infinite ranges, such as in the case of these two functions depicted here, the cubic function and the quadratic function x squared. Notice that in the case of x squared, we have two inputs, namely -1 and 1, that have the same output. What this translates to graphically is the fact that if I were to draw a horizontal line, then it would cross the graph of x squared twice. This is a very simple test for telling whether a function is one-to-one or not. If you're in possession of the graph of a function, and note that these are both indeed functions, because if you recall, the test for whether a graph is representing a function or not was called the vertical line test, and both of these functions do indeed pass the vertical line test, in that there is no vertical line that would cross either of these two graphs more than once. But notice this one, the graph of x cubed, also passes the horizontal line test, meaning there's also no horizontal line that would cross it more than once. This tells you that f of x equals x cubed is a one-to-one function, whereas clearly f of x equals, or g of x equals x squared is not, because we can see that there are many instances where two inputs will have the same output. We've only depicted two pairs of input outputs here, but notice 2 would go to 4 and -2 would also go to 4. So there are countless examples of showing this, especially because of the symmetry of x squared. So the fact that f of x is x cubed tells us that it has an inverse. We'll discover by the end of this video how to actually find the definition of that inverse. For the time being, I'll just tell you that it is the cube root of x, and we'll have a procedure which will show us how to find that. One thing I want you to note is that you only test for one-to-oneness, meaning you do a horizontal line test only after a relation has passed the vertical line test, putting it in the class of functions. We don't talk about one-to-one relations, we only talk about one-to-one functions. So to be one-to-one, you have to be a function first. So make sure that a graph passes the vertical line test before you do a horizontal line test on it to see if it is one-to-one or not. So recall that if a function is indeed one-to-one, and let's say the function f sends the input x to output y, we know that the inverse is going to do the exact opposite and send the output y back to x. So notice that this means if I were to start with x, apply the function f to it, that means I start here and go there, and then follow that by applying f inverse. In other words, if you recall from the last video, this is a composition of f inverse and f. I would always get back to x. On the other hand, if I start with y and apply the function f inverse to it first, I would end up here, and then if I follow that by an action of f, I would get back to y. So notice this canceling effect they always have on one another. Basically, the two inverse functions will always just give you back to the original input. Now, there's a very interesting relationship between the graphs of two inverse functions, because notice that if AB, the point AB, such as the one depicted here, is actually on the graph of a given function, then that means BA is going to be on the graph of f inverse. Why? Because if f of a is equal to b, this is what we mean by saying AB is on the graph of f. Notice that f inverse of b is necessarily going to be a. That's the way inverse functions work. If f sends a to b, f inverse is going to send b back to a. So therefore, whenever AB is on the graph of f, that means BA is going to be on the graph of f inverse. So we have this situation here, which creates a very interesting symmetry with respect to the line y equals x. So this gives us a way of obtaining the graph of an inverse function if we know the graph of the function itself, or vice versa. If we know f inverse, we can find the graph of f, and we'll take a look at that in more detail soon. So here we can see the two inverse functions that we discussed earlier. F of x equals x cubed and f inverse of x equals the cube root of x. Notice how beautifully symmetric the two graphs are with respect to the line y equals x. You can see x cubed here in red and the cube root of x here in blue. And we mentioned that a function like x squared is not one-to-one, so that it does not have an inverse. However, let's look at an interesting thing that we can do to maybe bring some hope to x squared as far as having an inverse as well, and that's called restricting the domain. Okay, so here in the middle we have the graph of x squared. Clearly it fails the horizontal line test, so it is not one-to-one. However, if I were to restrict myself to only looking at the part to the right of the y-axis or the part to the left of the y-axis, such as we are looking at here, then we would obtain two new functions with restricted domains that are one-to-one, such as here I'm taking the function g of x and I'm creating a new function g1 of x, but I'm only going to define it for all non-positive numbers. That means all numbers less than or equal to 0, all inputs less than or equal to 0. In this way, I have taken a function that is not one-to-one, and by restricting its domain to only this part, I've created a one-to-one function. Notice that this graph now does pass the horizontal line test, and we can in fact look at the mirror image, and this will be the graph of the inverse of that function, and this is defined by negative square root of x. Now on this side here, we're taking this right half of the graph of x squared, and we're doing the same thing. We're realizing that the red piece here is, and of course these keep going forever, but what we see here is clearly one-to-one. It passes the horizontal line test, and the mirror image with respect to the line y equals x this time will be this blue curve, which is actually defined by square root of x. All right, so the procedure for finding the inverse of a function given its graph is simple. Let's say you have the blue graph here given, and you're trying to find the red graph, correct? So here's what you do. On the blue graph, pick a few points. Notice I've taken this point, this point, this point, this point, that point, that point, and these other 2 points. Then what you do is what's called reflect it with respect to this green line, which is the line y equals x. Let's just focus on one. The way reflection works is very simple. If you've ever been into art, you already know how to do this. Basically, you take the point and you drop a perpendicular to the line of symmetry or the mirror, and you measure that distance, and then you extend that perpendicular exactly the same distance till you get to this point. Keep a tab of the, keep a record of that point. then go do the same thing for all the other points on the blue curve that you had marked as samples to reflect. So to reflect this point, we do the same thing. We drop a perpendicular to the line of symmetry and then keep going exactly the same distance and put a point. Now, the interesting thing is that when you reflect a point that is already on the mirror, think about it. What's the reflection of a point on a mirror? It's itself, right? So those don't need any kind of special action. They're going to be their own mirror images. Now we go to this point, we do the same thing. We drop a perpendicular to the green line and extend. And this way we do that with all the points that we had chosen. Again, here we have a point that's its own reflection because it's on the line of symmetry. And then we do this one. So notice we obtain this point, that point is already there, but it is obtained nevertheless, and this point. Now if we just draw a nice smooth red curve going through those points, we will have found the reflection of the blue graph. So in other words, you have to imagine that the red one was not there and I put it there. Now if I was trying to do this by hand, you would never see anything as beautiful as what you see here. So be glad that I utilized some assistance from Desmos to present this to you. All right, so that's how you find the graph of a function, an inverse function, given the function's graph as a starting point. Now, the graphic method is beautiful because it's very intuitive and it gives us a real visual appreciation for inverse functions, but we really are going to be more interested in the algebraic method of finding the inverse of a function given its definition. So for example, here we have a one-to-one function, f of x equals 3x minus 4. Of course, you know that's a linear function. If we take a quick look at its graph together, let me bring up Desmos. All right, so here we have the graph of f of x equals 3x minus 4. Of course, this is very easy to graph because you know the y-intercept is -4, so you start there. Of course, 0, -4 is the correct way of saying the referring to a point in the plane. And then the slope is 3. That you can write that as 3 over 1. So that means you go up 3 units and then right 1 unit and you'll end up with another point. Then you can quickly graph your line. Now, notice that it definitely a linear function like this will pass the vertical line test as well as the horizontal line test. So it is definitely a one-to-one function. In fact, the only linear functions that are not one-to-one are of this variety. Let's look at, for example, y equals, say, 5. Notice this graph here would obviously, it is a linear function because it's of the form f of x equals 0x plus 5. So it is in the form, it can be put in the linear form, which is referred to as slope-intercept form. But notice that it would miserably fail the horizontal line test because there is a horizontal line, namely itself, that crosses it many times. In fact, infinitely many times. So those are the only linear functions that are not one-to-one. And you may be thinking, hey, what about vertical lines? Well, vertical lines are not a part of the class called linear functions anyway, because they miserably fail. Let's take a look at one real quickly. Let's look at x equals 5. Notice that does not represent a function at all because it miserably fails the vertical line test, because there's a vertical line, namely itself, that crosses it infinitely many times. So it's not a function to begin with. And remember, we only discuss one-to-oneness with respect to functions. So that discussion is moot when it comes to vertical lines. All right. So we know that f of x equals 3x minus 4 represents a one-to-one function. And here's the procedure for finding the inverse. We're going to find the inverse. We're going to verify that it is in fact the inverse using a test point x equals 3. Then we're going to show that this relationship, this composition relationship, works for both directions. And finally, by doing so, we have proven actually that the two functions are inverses. When we do a demonstration for just one point, it's nice to kind of convince us we probably have the right inverse, but when we do this, we go beyond demonstrating. We actually prove that they're inverse functions. So for the first step, all you do is you go ahead and you replace the f of x with y. And the point is, we know what y is in terms of x, right? So if we can find out what x is in terms of y, we've basically found our way back. So that's exactly where we're headed. For step 2, we're going to go ahead and take this and we're going to solve it for x. So I move the -4 to the other side, and we get 3x equals y plus 4. Notice I just turned them around just to make it so that the x is on this side for aesthetic purposes. Otherwise, it's the same thing. Whether you say y plus 4 equals 3x or 3x equals y plus 4, they're the same thing. And now we're going to go ahead and solve this for x. So we get x equals y plus 4 over 3. You're, for all practical purposes, done. You have found the way back. So all you do at this point is go ahead and call that f inverse of y. Now, we could leave it just like that, and this would be a completely correct representation of the inverse function. It's just that usually we like to write functions with an input of x rather than y. So when you change all the letters in a given functional definition, then that letter is called a dummy variable. So right now, I can take these y's, I can replace them with any letter that I want, A, B, C, D, X. So I choose X because that's the standard input for a function, and I change both of them to X. So notice, it's really important to understand the step from here to here is optional, and it is a cosmetic step. So this is a perfectly legitimate result for the inverse function. But most textbooks will go ahead and go with this step and represent it using x instead of y. So now we're going to test it for 3 and see if it works. So the first thing we'll do is go ahead and find what f of 3 is, which is going to be just, here's f of x. So f of 3, wherever we see x, we're going to substitute it with 3. So we get 3 times 3 minus 4, which is 5. Now, if we have found the correct inverse function, we know that f is sending 3 to 5, right? So the correct inverse function should do what? It should send 5 back to 3, right? So let's test it. Here is the definition of f inverse of x. We're going to evaluate it for 5. Notice, what does f inverse do? What is the action of f inverse? You feed it an input, it adds 4 to it, and then it divides by 3. So what is f inverse going to do to 5? Well, it's going to do what it always does. It's going to add 4 to it, and it's going to divide by 3. So wherever you're seeing x, you're just basically replacing it with 5. And notice we end up with 3 as we were hoping, because remember, f sends 3 to 5. So f inverse should send 5 to 3. And it did. So this was a nice demonstration that we're more than likely in possession of the right inverse. But this would not constitute a proof. A proof would have to be much more general and show that this happens. In other words, whenever x sends, whenever the function f sends an input to an output, then f inverse should bring it back. So this is what we're going to check here. So here x, we start with x, we apply the function f, and then we apply f inverse to make sure. In other words, start with x, apply f, and then follow that by applying f inverse. That should bring you back to x. So notice that f inverse of f of x just means f inverse of that, because that's what f of x is. So 3x minus 4. So now we need to do the action of f inverse on this input. Now, what is the action of f inverse? Remember, to take whatever you feed it, add 4 to it, and then divide by 3. So now we're going to do that with this input. So we're going to take 3x minus 4. We're going to replace x here with 3x minus 4, and then add 4 to it, and then divide by 3. So notice we end up with this. Now the 4's cancel out, the negative 4 and the positive 4, and we get 3x over 3, which is x, as we hoped. We also want to do it the other way. So we want to start with y, apply f inverse to get to x, and then follow that with f to make sure that brings us back to y. So we want to show also that f of f inverse of y is also going to be y. So we take f of the inverse function y. So we're using this version here for the fact that it works out much nicer with this diagram if we use y. So f inverse of y is y plus 4 over 3, and f of f inverse of y is just going to be f of that, which is just what f inverse of y is. Notice now we need to apply the action of f to this input. Let's go back to f. Notice right here, what does f do to an input? It multiplies it by 3 and then subtracts 4. So it's going to take this input, it's going to multiply it by 3, and then it's going to subtract 4. Now, notice these 3's will cancel out, so you end up with y plus 4 minus 4, which is just y, which is exactly what we were trying to show. So now we have gone beyond just demonstrating with one example, and we have proven that these two functions, when one followed by the other, will undo each other, which is by definition what an inverse function is supposed to do. And remember, that's a mutual relationship. Not only is f inverse the inverse of f, but f is also the inverse of f inverse. So it works both ways. Make sure you understand this simple example before we proceed. All right, so welcome to the last problem we're actually going to look at, because there's not a whole lot to do here, but a whole lot to understand. So this is one of those sections that's not long in length, but deep in concept. So you really have to make sure you absorb the material. Now, here is another function, and if you watch the last video, you will recognize this, because this was the last example we also did on the last video we did on functions in general, and we also applied the composition of functions to that function and what you'll find soon to be the inverse of it. So let's go ahead and see how we can find it, though last time we were given this inverse. This time we're going to see actually how to find it. Then we're going to do a test point. We're going to test whether we have the right inverse function for x equals 13. Then we'll go ahead and proceed with proving the fact that they are inverse functions by proving that these two compositions end up giving us just what we start with, x and y. All right. So remember, step one, we're going to replace f of x in the original function with y. So instead of having f of x equals cube root of x minus 5, we're just going to write y equals the cube root of x minus 5. If you remember, the next step was to go ahead and solve for x. Remember, that means we're going to have to cube both sides. So we know that when we cube this, we just get x minus 5. When you cube that, you get just y cubed. Notice I switched the sides again to get the x on this side, because we're going to be solving for it. It'll look nicer if it's on this side. All right, so now we're going to go ahead and move the -5 to the other side. So we get x equals y cubed plus 5. And we now just go ahead and replace x with f inverse of y. So here we have our inverse, but remember, oftentimes in textbooks, in my math lab, etc., they're going to expect you to give the answer with x as the input. So now just replace all the y's with x's. You can do that with any kind of a function because the name of the variable is a dummy variable. That means you can use any letter as long as you substitute all of them. Remember, this is crucial. If you're going to treat a variable like this, and call it a dummy variable, that means you're going to have to change all the instances of it to another variable. All right, so here's our inverse function, and now we're going to test it for x equals 13. So remember, first we're going to discover what f of 13 is. So when we plug it in, we get the cube root of, instead of x minus 5, we're going to plug in 13. So we're going to replace x with 13. So we get the cube root of 13 minus 5, and that's 8. So that's the cube root of 8, which is 2. Now, if this is the correct inverse function, since f is sending 13 to 2, our inverse function should send the 2 back to 13. So let's see if it does. F inverse of 2, remember, that means here in this definition, wherever you see x, replace it with 2. Notice that's going to be 2 cubed plus 5. And 2 cubed is 8 plus 5 gives us 13. So we just did a demonstration with just one input, which showed that when f sends 13 to 2, f inverse doesn't in fact send 2 back to 13. Now here we're actually going to prove it in general. So we're going to start with x, we're going to apply f to it, then we're going to follow that with f inverse. So in other words, we're going to start with x, apply the function f, then we're going to apply f inverse, and if all is well, we should get back to x. Let's see if we do. Now, f inverse of f of x just means f inverse of what f of x was, which was what? Cube root of x minus 5. So that's just f inverse of cube root of x minus 5. Now we need to apply the function of f inverse to this input. What does f inverse do to whatever input you feed it? It cubes it and then adds 5. That's what we mean by the action of f inverse. Remember, functions are rather boring characters. They do one thing and only one thing, but they do it consistently. Like this particular function, f inverse, has only one action. No matter what you feed it, whether you feed it x, 5, 2, square root of 7, it doesn't matter. Whatever you feed it, it's going to cube it and then it's going to add 5. So now you want to feed it this expression here, which is the definition of f. So it's going to do the same thing. It's going to cube it and then add 5. So you're going to end up with cube root of x minus 5 cube plus 5. Now remember, the cube root of a radicand cube is just going to give you the radicand. So you just get x minus 5 plus 5, which is in fact x. The only thing left to do is to verify that if we start here, apply the function f inverse, and then follow that by applying f, we should get back to y. Notice that that means f of f inverse of y. Now, f inverse of y, we know is y cubed plus 5, right? So we end up with f of y cubed plus 5. Now we need to do the action of f to this input. Let's go back to f. Remember, f of x is the cube root of x minus 5. So the action of f is whatever you feed it, it's going to the cube root of that which you fed it minus 5. Now you're going to feed f y cubed plus 5. So what's f going to do? It's going to take the cube root of y cubed plus 5 instead of x and then subtract 5. These 5s will cancel out. So we get the cube root of y cubed, which is y. Notice we could have done this with x as well. We could have said f of f inverse of x equals f of f inverse of x. Using x would have been x cubed plus 5, and then we do the action of f to x cubed plus 5, so we get the cube root of x cubed plus 5 minus 5, which is the cube root of x cubed, which is x. The only reason I chose y, because with this visual here, the y would work so much better. So, and from a purely mathematical point of view, this is actually the preferred form, but this is the form just to fit the norm, that's all. So basically, this is what functions and their inverses are all about. And remember, anytime you have a one-to-one function, meaning a function that passes not only the vertical line test to be a function, but the additional test called the horizontal line test, this procedure will result in your ability to find its inverse. The function that whatever f takes an input to will take that input and output and bring it back to the original input. That is what inverse functions are all about. So this should do it for us today, and be safe until our next meeting.